This is Mr. Bear, and I want to show you how to do the lab molecular geometry problems. All the problems begin with you drawing the Lewis structures, then identifying the electron domains, and then from the electron domains, the bonding domains, you identify the molecular shape. What we're going to do is I'm going to show you the Lewis structure first for each molecule, do the count of the domains, and then I'm going to move to the name of the molecule and whether it's polar or not. I'm going to begin with our first problem, which is CH3Cl. In this particular structure, I'm going to first follow the method that I've taught you where I count the number of valence electrons for each atom that's bonding. When I look at this, see that carbon has 4 valence electrons, each hydrogen has 1, there's a total of 3 of them, so that's a total of 3 valence electrons. Chlorine has 7, add that up, I get a total of 14 valence electrons. So, now I have to identify who the center atom is. The center atom is either written first in the formula, which is about 99% of the time actually, or it's the atom that has the most unpaired valence electrons. Carbon will always be in the center for the molecules we practice. And again, we're doing what are called simple molecules. Simple means there's a center atom and then everything else branches off of it. So I'm going to begin by putting carbon in the center, and I'm going to connect all 4 of these atoms here because there's 3 hydrogens, 1 chlorine, that means there's 4 of them. Spread them out evenly like I'm doing right now. And then I'm going to add up how many electrons I use to connect all of them. I use 2, 4, 6, 8 to bond all of those exterior atoms. So I'm going to take away 8 from the 14, and then I'm left with a total of 6 valence electrons. So right now I've got 6 valence electrons left after I connected them all to the central atom, and I have to spread them on the outside first. So I can't spread them on the hydrogen because remember, there are exceptions for our octet rule. Remember the exceptions for going lower than the octet rule. If you're going lower, it's going to be hydrogen, which only needs 2, or boron, which only needs 6. So these are okay, so I'm going to put my 6 electrons on chlorine to make an octet on chlorine. So 2, 4, 6, I've made my octet. I now no longer have any more valence electrons. That's the correct Lewis structure. Again, you could have drawn this in a different arrangement. It could have had the Cl on top or the right or the left. Doesn't make a difference. Okay, now we have to count the number of electron domains. So if it's a single or a double bond, a triple bond, or a pair by itself, it counts as a domain. This molecule has 1, 2, 3, 4 electron domains, and I'm using ED to represent electron domain. Now if I'm counting bonding domains, what I do is I circle all of those electron domains I circled. I'm going to circle all the ones that were bonds and not lone pairs. 1, 2, 3, 4. 4 bonding domains. Now what I have to do, and I actually have to run over to go get one, is I've got to go get a chart that you should be using, which is on your covalent bonding help sheet. And on the back, this chart, except for the examples, is going to be provided to you on your test for identifying the molecular geometry. So in this one, it has 4 electron domains. It has 4 bonding domains. So the name of the molecule is tetrahedral. So I'm going to write that out. This is a tetrahedral molecule. Now, I have to identify what its bond angles are. The bond angles for tetrahedral, you can see, just go right across tetrahedral, then 109.5. And actually, on your chart, it shows you a little bit of a 3-dimensional picture of what this molecule looks like. And we can see it right there. That's kind of what this shape would look like. Now, the question is this a polar molecule or is it not? Well, if it was symmetrical, meaning I had all H's around it, it would be nonpolar. But I have a chlorine here. Chlorine's the most electronegative, so electrons are going to be shifting in that direction. This counts as a polar molecule. Again, you might want to use one of my simulations that I have links to on my website to help you understand these concepts. So I actually have on here one that's very similar to this. I have oh, wait, do I have the same one? No, I don't. I have CH3F. So imagine that F is a chlorine. You can see that it's a polar molecule because it doesn't have the symmetry. Electrons are being pulled to one side so that it's partially negative on one side and partially positive on the other. Okay, moving on. I'm now going to move a little bit faster when it comes to drawing the Lewis structure. The Lewis structure we should be decent at, so I'm going to draw it a lot faster. If you have more individual questions, please see me on tutoring. So that was the first one. The second one is ASH3. ASH3, arsenic trihydride. Arsenic has 5, hydrogen has 3. All 3 of those hydrogens total have 3, so it has 8. Arsenic's my central atom, so I'm going to put As, connect 3 hydrogens to it. Subtract the electrons I used to connect the 3 hydrogens, which is a total of 6. Then I have 2 left, so I have to put it here. That's my correct structure. Now, counting electron domains, I'm going to be using green to circle electron domains. I've got 1 here, that's a lone pair. I've got another electron domain here, another there, there. So there's 4 electron domains in this molecule. But there's only 1, 2, 3 bonding domains. Again, I go to my chart. I go to find how many electron domains, 4. There are 3 bonding domains. Shape of this molecule is trigonal pyramidal, and I see sort of a 2-dimensional representation of the 3-dimensional picture of this molecule. So I'm going to go ahead and label it as trigonal pyramidal. And also, one of the neat things is that the bond angle is right next to it, and you see that the bond angle for this one is actually the same as the other one. It's funny, the bond angles are determined by the electron domains, not so much the bonding domains. Now, is this molecule polar or not? So I'm going to go to that simulation and actually show you so you can see it in 3 dimensions a little bit better, but you're not going to have this on the test, so you need to make sure that you can do this on your own. So here is a molecule that's very similar to ASH3. That would be NH3, which is ammonia. And you can clearly see that trigonal pyramidal molecules are always actually going to be polar. You can write down always polar because they're going to have this funny shape where there's not any symmetry to that molecule. So one side of it's going to be negative and one side of it's going to be positive, which means it's going to be polar. So this indeed is a polar molecule. All right, moving right along. That's just the first 2. I got to move a lot faster here. We now have H2S. I'm going to go straight to the Lewis structure. I'm not going to talk about how to draw it. This is the Lewis structure for it. You should be able to draw it because it's a very simple one. If again I'm going to count my number of electron domains, doing that in green, I have 1, 2, 3, 4. So 4 electron domains. By the way, remember in the last one we said that the electron domains always tell us our bond angles. Well, it actually does. You can look at this chart and see that anything that has 4 electron domains always has a bond angle of 109.5. So I can already write down its bond angle of 109.5. And I'm going to count its bonding domains. There's only 2 bonding domains. So if there's only 2 bonding domains and there's 4 electron domains, then it is a molecule that we call bent. Now, all bent molecules are always polar because there's a lack of symmetry. If I look at this side, it's going to be more partially negative than this side because the electrons are being pulled in that direction. Both the partial negatives and the positives and this dipole are all redundant of one another, and it's basically saying that it's a polar molecule. Now, moving on. Let's go to the next one. Next one's going to be SO3. Now we're getting to ones where I'm going to actually show you and go a little bit slower on the Lewis structures. SO3 has, or sulfur has 6 valence electrons. Each oxygen has 6, so that's a total of 18 because there's 3 of them. So I have 24 valence electrons. Now, they both have the same number of unpaired valence electrons, so it's this one, the sulfur, that actually has, because it's written first, is most likely our central atom. Remember, we're only doing simple molecules, which means there's a center, and then everything else branches off that center atom. So I've used 2, 4, 6 out of the 24. Take away the 6. I have 18 left. Spread them on the outside before I go to the inside. 2, 4, 6. I have an octet there. 8, 10, 12, 14, 16, 18. I've used all 18 of my valence electrons left. I have none left. So I look at this molecule, and unfortunately in this molecule, I don't have an octet on everyone. Remember, certainly the only ones that can be less than an octet are hydrogen and boron. Sulfur is not in that category. So when you have no more valence electrons left and you don't have an octet on your central atom, that's when you know there's a double bond. Now is the point where you know it's a double bond. So what you do is these two, you can pick any pair of electrons from the oxygens, and then you can move it from being a non-bonding pair to a bonding pair. And then you have a structure that looks a lot like, no, it looks like this. Now your molecule may have been drawn where you have the double bond on this oxygen or that oxygen. That would be correct as well, because remember this molecule is in 3 dimensions. But this is the correct Lewis structure. Now for counting electron domains, I've got 1, Now notice this double bond counts as only one electron domain. This counts as an electron domain, this counts as an electron domain. So now I only have 3 electron domains, and I only have 1, 2, 3 bonding domains. Yes, that double bond only counted as a single bonding domain. So 3 electron domains, 3 bonding domains, 3, 3. My molecule is now trigonal planar, and it is a bond angle of 120 and looks kind of like this. So let me write it out. So it's trigonal planar. Our bond angle is 120. And let's take a look at it on the 3-dimensional space. So if I go to my polarity simulation, you'll see on the polarity simulation, if I pick a molecule that's trigonal planar, like, oh, I don't know, let me find one, like BF3. No, here's one, yeah, BF3. BF3 is trigonal planar. Uh-oh, come on, load. There we go. And whenever you have a trigonal planar molecule, it's sort of like a tug-of-war on the center atom oftentimes, or it's the center atom tugging on the other ones. It's often an even battle. And if they're all the same atom on the outside and it's trigonal planar, it's always going to be nonpolar. But if I have a molecule where they're not the same on the outside, here's a trigonal planar one, but this atom is very different than these two. This would be a polar molecule. So polar, nonpolar. So if we look at this, we have the same atom all on the outside, so it's going to be non-polar. Okay, now moving on. We're going to go to the next one, which is SO2. SO2 is very similar to SO3. We know we have 6 here, we have 12 here. It's very similar to the last one. We've got 18 valence electrons total. We know who our center atom is, it's the sulfur. And I'm going to connect the 2 oxygens. And I've used 4 of the 18, and I have now 14 valence electrons left. And I'm going to spread them on the outside first. 2, 4, 6, 8, 10, 12, 14. So when you fill up your octets on the outside, you now have to move to the inside, and I have a pair on the inside. So I've used all 14. Now remember, sulfur needs to have an octet just like the oxygens do on the outside, which means that if I don't have any valence electrons left and I need an octet on the center, I have to make a double bond. So I will do that just like the last one, and when I do that, I end up with a structure that looks like this. And again, your double bond could have been on that side as well. Now, counting electron domains, I have 1, 2. I only have 2 electron domains. Turns out that oh wait, always double check yourself, because notice I almost made a mistake. I almost didn't include this lone pair as an electron domain. I have 3 electron domains. Always double check yourself, even I make mistakes. So the number of bonding domains, 1, 2, I have 2 bonding domains in this structure. 3 electron domains with 2 bonding domains is bent. But again, notice that it's the electron domains that determines our bonding, so it's 120. So we've got, and again, you can use that chart in your test, we've got 120 degrees for our bond angles. We have a bent structure, and I told you that bent is always polar. Done deal. All right, moving on. Next one's going to be H2CO. I believe I actually showed an exact picture of this on the 3D molecular simulation on polarity. So quickly do this one. There's 2 valence electrons for each, or 1 valence electron for each hydrogen, so 2 total. 4 for the carbon, and 6 for the oxygen. So I have a total of 12. Carbon's got to be my center because it's got the most unpaired valence electrons. Carbon's almost always the center. Connect it like that. I've used 2, 4, 6 of the 12. I have 6 left. Spread it on the outside first. 2, 4, 6. I have none left. I have an octet here, duets here, so these are happy, that's happy. But I don't have an octet on carbon. Carbon needs an octet. And again, if you don't have any electrons left, you have to move something in for a double bond. So your structure ends up looking like this. That's the correct structure. Count the number of electron domains. We have, again, you look at only the center atom for counting these domains. 1, 2, 3 electron domains. You have a total of 1, 2, 3 bonding domains. So you end up with a shape that is trigonal planar. Now trigonal planar, if they were all the same atom on the outside, it would be nonpolar, but they're different, so it's polar. And again, trigonal planar with that 3 electron domains is always 120 degrees. So there's my molecule right there. Let's go to the next one. Next one's going to be O3. O3 is a little bit trickier. It's ozone. It's actually a major pollutant in our atmosphere. Each oxygen has 6, so that's a total of 18 valence electrons. So one of those oxygens has to be in the center, so I'll put one in the center, put the other 2 on the outside. I've used 4 of my 18, so I have 14 valence electrons left. Spread them on the outside first. 2, 4, 6, 8, 10, 12. I've made my octets on the outside, but I still have 2 left. Have to put it on the center. Put the 2 in the center. I have none left. I look at it and I go, I still don't have an octet on the center. I only have 2, 4, 6. So this means I need to have another 2. That means I've got to make a double bond. My structure ends up looking like this. Same story as before. When you look at it, you could have had the double bond on the other side. Doesn't matter. It's a 3-dimensional molecule. We have 1, 2, 3 domains, 3 electron domains, which instantly tells me that it's 120 degrees. But I only have 1, 2 bonding domains, which means that I have a bent structure. And if it's bent, it's always polar. Okay, that's ozone. Let's move on to the next one. Carbonate. Carbonate is a very popular one to do for structures. We've got 4 valence electrons for the carbon, 6 for each oxygen, so that's a total of 18. Next, I've got these 2 electrons I add down here, so I have a total of 24. Connect them like this. Doesn't matter where you spread them. I used 2, 4, 6. So I have 18 left. Spread them on the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18. I now have my octets on the outside. Don't have any left, but I don't have an octet on the center, so one of them has to be a double bond. So I end up with a final structure that looks like this. And when I count my, oops, forgot the double bond right there. Count the electron domains, 1, 2, 3, 3 electron domains. Count the bonding domains, 1, 2, 3, 3 bonding domains. I look at this and I go, oh, okay, so if I use my chart, 3, 3, trigonal planar, 120. So trigonal planar. And if it's trigonal planar, if they're all the same on the outside, we know it's nonpolar. And it's 120 degrees for each of those. Okay, next one. That's carbonate. Now we're getting into the ones that exceed the octet rule, and I'll show you how I know that when I start solving these problems. So SF4. Sulfur has 6 valence electrons, each fluorine has 7. 7 times 4, 28. I end up with 34 valence electrons, quite a bit. Sulfur's got to be my center. It's got the most unpaired, plus it's the first written in the formula. So I put the S in the middle, spread out my fluorines. I have to use 8 valence electrons because each of these sticks are 2. So I'm going to take away 8. I'm left with 26. Spread it on the outside first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've used 24 of my 26, but I still have 2 left. So when you're in a situation where your center atom, this one, is in the 3rd period of the periodic table or lower, and if you don't know what a period is, remember periods are the rows of the periodic table, and this would be the 3rd period for our nonmetals that are covalently bonding right here. And it's because they can dap into the d orbitals, they can actually exceed the octet rule. So I've got the 3rd period or lower element in the center. I've got 2 left and nowhere else to put them. Always put them in the center atom. So I put 2 in the center atom. Now I have none left. I've violated the octet rule, but that works because this element is 3rd period or below. And now I got to count out the electron domains and bonding domains. Number of electron domains, here's 1, here's another, here's another, here's another, there's another. That pair by itself counts. So I have a total of 5 electron domains. Now I got to count the bonding domains. 1, 2, 3, 4. I have 4 bonding domains. Got to go to the chart on this one. So it's actually on the backside. Got a total of 5 electron domains, 4 bonding domains. My molecule is actually called a seesaw shape. Actually, we can see the example molecule right here, SF4, which we just drew. So it says that it is seesaw. Seesaw is always polar. You can take a look at it. Look how there's not much symmetry. You would need something on the right side as far as an atom to have symmetry. So it is indeed a polar molecule. And mostly you have a bond angle of 120, but also 90 and 80 if you look at it from all the different bonds in this molecule. Okay, now, next structure, next two are some serious violations of a rule we talked about, which is noble gases not being able to bond. Turns out with research, we've discovered that there are certain noble gases that can bond. Xenon's one of them. If you're doing the Lewis structure with a noble gas, it does seem initially tricky because you're like, how many valence electrons does this have? It's already happy. It's full. It's got 8. Well, it does have 8. And when you do your count, do it in the way that you've always done it. So there's 7 for each fluorine, so that's a total of 14. So we have a total of 22 valence electrons for this molecule. And xenon's written first. It's going to be, in the center actually. You're going to draw the fluorines on the xenon. Take away 2 4 electrons from your total of 22, so you have 18 left. Spread it on the outside. 2, 4, 6, 8, 10, 12. So now I have 6 valence electrons left. Now, when you deal with these large numbers, it's always good to go back and double check your work. So that does have 8. That does indeed have 14 for those 2. That is indeed 22. Take away the 4 from my bonding. Yes, that's 18. Take away the 12 from these. I have 6 left. So where do I put them? Can't put them on the outside. Xenon is really low below the third period, so it can violate the octet rule. So here I go. 2, 4, 6. So I actually have a total of 1, 2, 3, 4, 5 electron domains. But I only have a total of 1, 2 bonding domains. Use the chart. 5 electron domains. Number of bonding domains 2. My molecule is actually going to be linear, just kind of like I drew it. Now linear molecules like this always have a bond angle of 180 because it's in a line, and also it's the same on both sides, so you've got some symmetry to it, so it is indeed nonpolar. Okay, now let's go to a similar one, the last one, which is xenon tetrafluoride. Counted up in the same way. We had 8 here. 7 times 4 is 28. So 8 plus 28 is a total of 36. Put the xenon in the center, spread out my fluorines. And once I spread out the fluorines, I use 2, 4, 6, 8. Take the 8 away from the 36. I'm left with 28 valence electrons. Spread those on the outside first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've used 24 of my 28. I have 4 left. Violate the octet rule, put them in the center. So when you count your electron domains, you have 1, 2, 3, 4, 5, 6. You have a total of 6 electron domains. You have a total of 1, 2, 3, 4 bonding domains. Look at your chart. 6 electron domains, 4 bonding domains. You have a molecule that is called square planar. Now a square planar molecule has angles of 90 degrees if you look at your chart, and actually it looks a lot like this. In fact, I believe that's our example molecule right there. They all pull on each other evenly. You have some symmetry. It is a non-polar molecule. If you have any other questions, please see me for tutoring.